So here we're going to be looking at the difference between osmosis versus osmolarity. Just hopefully a quick little thing to help you understand this for your lab reports and being able to do some calculations and whatnot. So osmosis, let's remind ourselves quickly of the definition of osmosis. Osmosis, well, this is just the diffusion. Remember, when you hear the word diffusion, think passive. So everything in the universe is trying to go from an area of high to low. Diffusion, things are trying to go from an area of high to low. And this is just the diffusion of water, which means that water wants to move from an area of high water concentration towards an area of low water concentration. And the way to always try to remember that is pure water versus salt water. Pure water has a high water concentration, and salt water has a lower, relatively, concentration of water compared to pure water. So if we were to put pure water and salt water together, the pure water would try to move towards that salt water. And if we had a membrane in between, then the pure water would want to move towards the salt water. Where water moves towards particles, right? Things like salt, things like proteins. And particles, well, that's just a party. In class, I always say, particles, we just can change that. We got ourselves a party. So in other words, water always wants to go where the party's at. So you just find out where the party is at, where are there more particles, and wherever that party is at, water is going to move towards it. All right, so water moves towards the party. That's a nice little way to try to remember osmosis, is that you just find parties and water wants to move towards that. Well, that's what osmolarity is for. Osmolarity is really, it's a measure of the concentration based on the number of particles of a particular substance, a molecule, whatever you're putting into your solution. So osmolarity, well, this is just a measurement of the concentration of particles. In other words, it's a measurement of the party. Wherever there's a great degree of osmolarity, that's where the party is at. Osmolarity can be calculated. Okay, osmolarity is just a molarity, where molarity equals moles per liter, or a mass divided by a volume. And then if we want to add osmolarity, well, it's a measurement of the concentration. So we go osmolarity, capital O, lowercase s, capital M, is equal to moles per liter, and it's a measurement of the particles. It's a measurement of the number of particles. It's a measurement of the party. Now, calculating the number of particles of a molecule is one of the main reasons why I'm putting together this little video, because it's not always intuitive of what to do. But the reality is that different molecules can break apart in water, and some molecules don't break apart in water. When molecules break apart in water, we call it dissociation. So the particles here, this is a measurement of dissociation. And if you recall from class, dissociation occurs only if we have an ionic bond. So when we're trying to measure the number of particles, it's relative to the number of ionic molecules. In order to be able to figure this out, let's just remind ourselves real quick. We're going to write down a list of ions. List of important ions. All right? sodium, potassium, calcium, chloride, hydrogen, and then some other ones like bicarbonate and phosphate. Right? These are all important ions in the human body. So anytime that we see these ions in a molecule, we can assume that that molecule at least will dissociate that ion in water when placed in water. So for instance, if I had a molecule like sodium chloride, if I put that salt into water, what I want to do is I want to say, what ions do I have available? Well, there's a sodium cation, right? So I see a sodium cation, and what else do I see? I see a chloride anion. Each ion that you see is a party. Each ion that you see is a party. So how many sodium cations do you see in sodium chloride? Well, this is 1 sodium. And what else do we see? We see 1 chloride. So how many total particles are there? If I put sodium chloride into water, it would dissociate. It would get ripped apart into 1 sodium and 1 chloride. And now we have a total of 2 particles. Let's do another one. Let's go with calcium chloride. Calcium 2 plus is a cation. There's our chloride, there's our anion. But let's rip this thing apart, because in water it dissociates. And what are we going to end up with? We're going to have 1 calcium cation, and here's the trick. Because calcium's a 2 plus, it required 2 chlorides to bind to it. So that's where the Cl2 comes into play. We have 2 chlorides. So how many total particles are we going to have? There are 3 particles. So we just measure the number of ions that we are counting. That's how we are going to determine the number of particles that are available. Let's do one more example real quick. We're going to do, let's do this one. C6H12O6. For those that maybe remember this is glucose. This is the primary monosaccharide that runs the energetics of your body. Here's the trick with this one. Carbons, hydrogens can be an ion, but hydrogens also form covalent bonds. Oxygen. Carbons and oxygens are not up here in our list of ions, and as long as the hydrogens are bound to carbons and oxygens, these are covalent bonds. So glucose is covalently bonded together. Therefore, if I put this in water, does it dissociate? No. This does not rip into 24 different ions, because these aren't ions. This is just 1 particle. It does not rip apart. There's no dissociation. Even though it's a big molecule, it's bigger than sodium chloride, that don't matter. It has to do with the chemical bond. If there's an ionic bond, then it will dissociate. If there's not an ionic bond, then it does not dissociate. So things like urea and glucose, these are just 1 particle. Versus something like sodium bicarbonate. Well, sodium is a cation, bicarbonate is an anion, so that would split into 2 particles. And why this is so important in the human body, in biology in general, is that maybe you'll see that we have osmosis as the diffusion of water. It's going to go towards the party. The bigger the party, the more water moves at a faster rate too. So what did you just find out about something like sodium chloride and calcium chloride relative to glucose? Is that calcium chloride has 3 particles, and that's the biggest party. Sodium chloride has the second biggest party, and glucose basically is just, not even a party. Which one of these is going to draw water, assuming they're all at the same molarity? Which one of these would draw water to the greatest degree? Boom, right here. It's the calcium chloride. How we can actually calculate this mathematically is kind of why I wanted to put together this little video for y'all. Is that, say for instance you have, it doesn't really matter, let's say we have 0.5 molar concentrations of calcium chloride, and then your professor says, calculate the osmolarity. So how do I go about doing that? Well, first off, we only start with molarity. And molarity is moles per liter. So that's not what we want. We want to get to osmolarity. So what are we going to have to do to this in order to get it to osmolarity? We're going to have to multiply it by the number of particles that are available. So calcium chloride, we just found out that calcium chloride dissociates into 3 particles. So to calculate this as osmolarity, we're going to take 0.5 molar of calcium chloride, don't forget your units, and you're going to multiply that by 3 particles. And what is that going to be equal to? That equals osmolarity. Up here, this is the molarity, but when we multiply it by the number of particles, we end up getting the osmolarity. So 0.5 times 3, that's 1,500 osmoles of calcium chloride. That's a big number because we had to multiply it by 3 particles. What if we started with a molarity of 0.5 molar glucose? Well, now if we want to do osmolarity, we're going to take that 0.5 molar glucose and we have to multiply it by the number of particles if I put glucose in water. Well, how many particles is glucose going to get ripped into? Well, it's not getting ripped at all. It's going to stay as 1 particle. So when it comes to osmolarity, this just stays, oh, I messed this up. I said 1,500. It's actually 1,500 milliosmoles, and that doesn't help you guys right now, so I apologize. This would be 1.5 osmoles, and we're going to go back and we're going to calculate it as milliosmolarity. But down here, 0.5 molars times 1 particle, that's just 0.5 osmolarity of calcium chloride. Now, regardless, sorry about this little, I just skipped a step. That's why we don't want to skip steps, because even I make mistakes on that. 1.5 relative to 0.5, I mean, which one's bigger? This one, and this 3 times bigger. The last thing we do want to be able to do is in all my problems, I say make sure that this is physiologically relevant, and that's what I did up here in my head, and that's what I'd like for you not to do. Don't do things in your head. Is we need to be able to calculate these physiologically relevant, which is not osmolarity, because everything that's happening in the body is happening at a much smaller level. These solute concentrations in the body are very low. Therefore, they are measured in milliosmoles, not osmoles. So in the body, we're always measuring things as milliosmolarity. Milli telling us 1/1000th of. So what we need to do is we need to take these calculations, like 1.5 osmolarity of calcium chloride, And we need to turn it into milliosmolarity. And earlier this semester, when we were doing dimensional analysis, I taught you guys if you start with a unit, it's not the final unit you want. What you do is you can write yourself an equation. Over here, we can write the final unit we want. We want this in milliosmolarity. Over here, now we are going to create a little box, right? This is going to be our calibration number. And we know that we want milliosmolarity as our numerator. So we write milliosmolarity here. This is what we know we want as our numerator. And what do we want to get rid of? Osmolarity. So we put that down here on the bottom. Now these units are going to cross cancel. And what we need to do next is put in our numbers. How many millis are there in a base unit? Well, there are 1,000 milliosmoles in 1 osmol. So now the numerator, 1,000 milliosmoles, equals 1 osmolarity. And the bottom, the denominator, is also 1 osmolarity. So now the top is equal to the bottom, and technically this square right here, this is just 1. And now we did what we want to do. So now 1.5 times 1,000 is 1,500 milliosmolarity, which is what I had up there when I skipped a step. We'll just do one more, and then we'll stop this. Let's go ahead and just calculate what's going on with glucose. This is just 0.5 osmoles of glucose, but we get to just do the same dang thing. Now we're going to multiply it by, well, we want our little equation here. We know we want this to be milliosmolarity. Therefore, milliosmolarity is up here on top. I didn't even realize I was off the page. I apologize. There we go. So milliosmolarity is up here, right? And down below is osmolarity. As long as our units end up how we want our units, then we are golden. And now we can stick in our numbers. It's just 1,000 divided by 1. So 0.5 times 1,000 is 500 milliosmoles. So calcium chloride, if I put in 0.5 molars of calcium chloride, that would be 1,500 milliosmoles. But if I put in 0.5 molar of glucose, well, that would only be 500 milliosmoles. So now the last little bit. Why is this important? Why do we care, Dr. H? I need to know. It comes to giving patient IV fluid. It's the primary reason you guys should care about this. If you give a patient an IV fluid of 0.5 molar calcium chloride, you're actually giving them 1,500 milliosmoles. Whereas if you give them 0.5 molar glucose, you're going to be giving them 500 milliosmoles. And this is the party. So let's draw what would happen in the human body. If I have a cell, we'll just say this is a red blood cell. The cells of the body are in homeostasis. They're happy for the most part, and therefore their milliosmolarity is 300 milliosmoles. That's happy. That's normal. That's what this cell is at. And then we dump in 0.5 molar calcium chloride. That's 1,500 milliosmolarity. That's a pretty big deal. Because now, where is the party at? Well, 1,500 milliosmolarity of calcium chloride. Calcium chloride is a non-penetrating particle because they're ions. They can't get across that phospholipid bilayer. So these are going to try to go into the cell. These particles are going to try to go from an area of high to low. They're going to try to go into the cell, but they are non-penetrating. They can't get in there, so they just bounce off. Now we do osmosis. That's the next step. Where does water want to be? Water wants to be where the party's at, and water goes rushing out of this cell towards the 1,500. Nasty. 1,500 milliosmoles would kill a person. Okay? Now, I'm not saying that 500 milliosmoles is much better, but I do want you guys to see the difference in what we just gave these patients. Because now, happy cells, 300 milliosmolarity. Outside the cell would be our glucose. Right? This one up here is calcium chloride. This one down here is going to be 500 milliosmoles of glucose. Now, glucose is non-penetrating because it's a big polar covalent molecule. It's going to try to get into the cell, but since it's non-penetrating, it bounces off. And water still leaves this cell. However, everything in the universe is trying to go from high to low. And the steeper the gradient, the faster things move. So which one of these is going to cause water to get sucked out of this cell faster? This calcium chloride. This is no bueno. So we'd have to actually dilute out this calcium chloride. You would not want to give them 0.5 molar. You'd want to drop that down. You'd actually want to keep it equal to what's happening inside the body. But this is why we need to do these calculations, is because of the results and the response of what's happening in the human body. So I hope this was helpful. I hope this helps you answer your lab report questions for my students. If anybody else is watching this, I hope it's helpful in regards to your class as well. All right, humankind, be human, be kind. All right, peace.